Thank you everyone for joining. My name is Mohit, and I organize this meetup to meet up with people and connect and network with people who are actually passionate about cybersecurity. Right. Um, this is a new meetup that we've started, and this is the second event that we're hosting. So thank you so much for joining. Yeah. We are actively looking. I'm actively looking for speakers for the meetup. So, in case you have something interesting that you want to talk about, something that you're passionate about in cybersecurity, and feel like you want to share to an audience, please reach out. I have a link for sharing in case you have a proposal that you want to go ahead and talk about. There's a page where you could submit a session. The details are in chat now. Let's get this started then. Today, I am going to talk about a specific type of cybersecurity threat that has actually caught the attention of the world lately, and that's very specific to because it was related to Linux. And Linux is sort of such an operating system that the whole internet is supposed to be running on it. Almost 75% of the infrastructure of the world is running on it. Yeah. The problem that happened was that the story convoluted in such a way that a loss of trust led to a very important tool in the Linux community being corrupted. I'm not sure how many of you are familiar, but Linux has a couple of tools that comes built in its repository and uh, in its whole ecosystem. When you install Linux, a couple of tools come in with it. Like if you do not install bare minimum, ping and other network tools come in, decompression and compression tool come in. One of those tools is xzutil, which is a compression and decompression tool, right? So just keep that in mind because that is something that has highlighted this threat to a whole new level now. Remember, this tool comes built in on a Linux machine, so you do not have to install it before or to use it. It just is there as soon as you install Linux. That's what makes this attack a bit dangerous. Now, software development in itself is not a very complicated thing, but over the years, we've started to realize that we depend on each other's code a lot more than people would want to admit. People want to understand that we make original code, but we actually don't make original code. We make code that is dependent on other people's code, and that kind of gives everybody a dependency. So for example, in this diagram here, if you look at it, the source code is created by a couple of developers. They built it, they package it, they release it in the wild for the consumers. But sometimes these these binaries, these source codes are released to the community back also. And then again, this goes through the whole cycle when developers borrow these dependencies and they move ahead and use these dependencies in such a way that it gives them a longer lineage. So the moment they get into and tap into the dependencies, they go ahead and tap into that ecosystem. And eventually, over the years, we've realized that we've got into a position where all code is mostly dependent on each other, and that's scary, and that's lovely in a sense too, because this kind of gives you an ecosystem where people have to look at each other. People have to take care of that one code. The scary part is if that one code is somehow compromised, the whole ecosystem, the whole internet is compromised. So if you see here, the people who develop, there's not just one developer, there could be a primary developer, but there are more than one developers. Dependencies in itself over the years have devolved into more dependencies, which again have more dependencies to it, and the changes goes on forever, which kind of gives you an impression that everything in the source community is connected. The reason why I've highlighted one of the main developers is because that developer is called maintainer in open source community. Open source community usually has one or more maintainers of their source code, and people borrow their code and try to use it, and this maintainer or the maintainers try to maintain and upgrade and add functionality eventually. Now, this process here that has been highlighted has a couple of drawbacks. First, in case one of the developers has a hidden agenda, which has come to light recently with the Ukraine and Russian war. People were taking sides, and then there is a technical warfare. A couple of developers from Sweden and some other European countries, they decided to make sure that their packages are not used by the Russian community. So they corrupted couple of node package versions, and these developers were not first time developers, they were experienced developers, which kind of led to a reputation breakdown, but in a sense not the breakdown of usage. People still use their packages, most of them don't even know why or what it happened. They open backdoors to their source code, they open backdoors to their channels, restricted access to Russians, and in turn gave this community, weaponized this community. Uh, sort of activity in such a way that they had their political agendas aligned to the technical agendas. This is just one form of it. Developers could be compromised in a number of ways, which was highlighted in XZ vulnerability 2, which we get to in a minute. Then there's code build, which injects dependencies. So let's say developers were okay, but then there are dependencies which were injected during the code build, which leads to another issue. In case one of those dependencies is compromised, or you're using a version that is compromised but was patched, you've hard coded it, you again have a product that is compromised to get started with. And in case that goes back to the cycle of creating another dependency, and there you can see this just spirals out of control very soon. The reason why this doesn't happen most of the time is because open source community has sort of a trust situation going on. The source code is available to everyone, which means everyone can look at it. Most people are not curious about the source code, but some are. Big companies are curious about it. They go ahead and check the code, they go ahead and go through it, try to replicate it. They do all sorts of stuff. It happened with a lot of database software. Ubuntu and Linux are examples of it. Apple took the source code, created a proprietary software. So the source code is available. And it kind of becomes a sort of shared responsibility that everybody is going to go ahead and go through the source code, get to know it, and maybe somehow using it. And maybe if there's something that they realize during the usage, they will give back to the community. Most of them don't. Sometimes people do, which happened in this case. Group immunity is something that in the open source community is very prevalent, because if something happens to one of the users, it will happen to everybody else. And that's one of the reasons why XZ and the other backdoor attacks eventually became a worldwide phenomenon. WannaCry and all that, uh, all those viruses and vulnerabilities were to such a global extent, right? Repositories and stars and scores, they're treated like reviews, as if people who are using it, the number of downloads that are happening gives you how popular that repository is. But it doesn't essentially gives you how safe it is, if you think about it. And because it's just a score, it can be spoofed with the proper technical knowledge. These things can be spoofed, and it might look like that you're doing something. I'll share one of the repositories which actually was hacked and eventually led to this situation. And plus, big tech and everybody else is watching what happens. So most of the times, these repositories, these softwares, they're scrutinized to such an extent, used so much extensively, that eventually something or the other obviously comes out, and people go ahead and share these updates, upstream requests to fix certain bugs. That happens. And that's what sometimes leads to a burnout for the maintainers, which happened in this case. And all of this that I'm trying to highlight led to something extraordinary, which kind of worried a lot of people about why open source security needs a fresh pair of eyes. This is a very famous diagram that's been a cornerstone of discussion on Linux community. That all of the modern infrastructure is usually built on somebody maintaining one particular repository at some corner of the world. The same thing happened with the XZ backdoor. XZ, the compression utility, as I told you, was built in Linux, is built in, and eventually it was just it's part of the operating system, so you do not have to install it. And most of these things that run on Linux utilize these compression and decompression algorithms. The reason why these things fail sometimes is because maintainers, they do not get paid for it. This is a hobby project. Yeah. The most of these good ideas, these packages, are a result of somebody having a very good idea, a good piece of code that they developed and they eventually wanted to share. And over time, it becomes sort of a moral responsibility to keep it updated. But it's just that, a moral responsibility. It's a hobby. Nobody pays open source developers. That's kind of a concern because time, if it's not justified by return, if it's just justified by goodwill, eventually leads to burnout. And that it happens, it does happen. People get burned out and they just lose track, they stop updating repositories, and it happens with a lot of big software. There are a couple of famous, or do I say infamous, supply chain attacks. I'm pretty sure some of you have heard about at least one or two of them. SolarWinds was the infrastructure management software. In 2020, updates were installed and updates had backdoor entry. I'm saying backdoor a lot, many times. I think I would explain it a little bit more. Backdoor essentially means granting access to the system without the user's consent. It, in simple words, a hacker or a malicious party or whoever that is that's trying to do this gets access to your device, your software, your built pipelines, or anything that deals with sensitive information that runs this software. Eventually leads to an open access. In case of XZ or most of the other softwares, it's root access, and root access is exposed and through processes that are already there. For example, in case of SolarWind, the updates that are updates generated by the SolarWind process. So in case a malicious code is introduced in the update, it would be executing as if SolarWind is executing it. And this was discovered very late, and a lot of companies were affected because SolarWinds is a huge company in monitoring. And the one that was highlighted most was Mimikast. In 2021, they had a email security. They had a vulnerability that was exploited, and that is how this thing just exploded, and people started noticing it. Another one was Asus computers updates again, because Asus updates its computers through its own proprietary wizard, and it creates a process. And because of that, the live update utility, the software was updated with the malicious code, and the way they did it was very smart. They first hacked their computers, their servers, and then it went through a certificate that had similar signature, which is not easy to replicate. It was a very complicated attack. When they did, after they had access with the certificates, they went ahead to update the vulnerability in their update software, which essentially gives them a leverage on a huge number of computers. So right now, instead of targeting the Asus servers, they targeted every computer that runs Asus update or Asus brand, which is scary in the extent of it, because these are not just personal computers. They are used in all kind of government agencies and sensitive situations. So all of those accesses were just open to everyone else. And that's why backdoors are especially dangerous. Then there is this which is a code coverage tool. It reads and updates report, and it creates a report about your code, updates it to a server. What people did, attackers, they hacked that script, that one script, and went ahead and added some malicious code to it. And what happened is that every pipeline that runs, or every code build that runs, usually has sensitive information in their environment variable. This is what this was targeting. The continuous integration pipelines, because they had production environment variables, which essentially means, if you think about it, means all the infrastructure that is deployed by that pipeline, all the infrastructure is now open because all their credentials are open, not just computers. For example, if this is going for cloud, so all your SQL servers, virtual machines, storage accounts that have maybe a key there, have their accesses open here. And the moment that happens, most of these things can be accessed over the internet. What happened with the XZ backdoor, the star of the show today. XZ backdoor is basically introduced vulnerability in the XZ software, a popular lossless data compression algorithm tooling, which is by default introduced in the format of the Linux operating system. Linux is the most used operating system. Around 75% of the world's infrastructure runs on Linux. And this software is available by default on that operating system, which essentially makes it very dangerous. The complexity of this attack is is worth exploring. And the reason why I wanted to focus on this one is because it's not just technical, it's social engineering that went into this. A lot of social engineering, a lot of time was invested, and a lot of trust issues happened after that in the community. Now, we have to understand this XZ utility is being maintained by just one person in one corner of the world. And that's his own responsibility. He doesn't have to do it, but he does do it. And because it's maintained by one person, they targeted him with the social engineering hack, and then eventually moved ahead and took over the whole software. The social engineering part was done with the help of comments. I'll show you more about these, but in a gist, there was an actor called Jigar Kumar who essentially went ahead and harassed the maintainer, all within the bounds of not calling it harassment. So he pushed it and made sure the maintainer, felt responsible for the software and felt guilty that he's not able to maintain it. For example, a couple of comments that they did was that it kept on continuously asking, is something maintained, or why hasn't he heard back about the update or submissions? Putting up false requests in order to gain attention, trying to update mailing list, trying to get attention from the maintainer so that they are not distracted to other things and they focus on this conversation. And he went ahead and continuously poked him about why these delays are happening, why you're not updating certain things. And during the process, he introduced another actor, which is Jia Tran, and introduced him in such a way that the maintainer felt like it might be a need to introduce somebody else to the repository so that they can take up the load a little bit. And Jia was kind of a technical person. It's not sure if it's one person or an agency, but the technical details of this person were nice. They was updating and sending a push request a lot too many times, which is one of the reasons why the maintainer actually trusted the person. The dev burnout actually was the second stage of social engineering. This is the stage where this person realized that he cannot do it alone. And it's an assisted track, because all these comments that were happening, they assisted him in such a way that he realized that there is too much work. For him, it's becoming impossible. So, for example, the couple of comments from the maintainer highlight what exactly happened. And if you look at it, he clearly says that this is an unpaid hobby project. So it's kind of his responsibility to update it, but it's not his only responsibility. And he also highlights that he is looking for a co-maintainer. So the need was developed, and then the need was fulfilled by another actor. The Jigger vanishes from the conversation eventually after harassing this maintainer, and another actor, Jia Tran, is introduced there, and he poses as a friend. He updates repositories, eventually, bit by bit, introduces malicious code, not at one go, but eventually maintains small integrations to the software. He rises up to such a level that he is now approving the pull request and publishing them to the repository. Right? There's a chronology around this. The account for Gia was created around 2021, and which is now not available. GitHub has banned the maintainer and the malicious actor, both from GitHub. Uh, He committed his first repository in 2022, and then it went ahead and created fake PR request and other other mechanisms to to go ahead and mask the changes that he was doing. So he introduced other actors who used to submit PR requests to go ahead and check what he was doing and what others were doing, just to give the whole process a legitimacy. And eventually, in 2024, around January, he introduces a malicious file in the gitignore and introduces encryption stage. This is very important because this is how the attack is triggered. So an encrypted stage is involved in the software now, which can only be triggered by an encryption, by a signature or a certificate. And fortunately, Andreas from Microsoft discovers this backdoor during a very lucky session of stress testing his SSH connections. He noticed that his software was, or the SSH connections were taking memory much higher than needed. And during investigation, he realized that there are more processes running in the background than SSH. And those processes were not necessarily documented, or what was not necessarily legitimate. This was a very lucky guess. And if you go to his Twitter, which is linked here, you will notice that he clearly mentions that this was just a lucky coincidence, and a very lucky indeed. Because if this would not have happened, I would show you again that this malicious code would have given access to every Linux computer on the world, in the world, sorry. Now, if you notice the timeline, this person took his time, like almost 2 years, to gain trust, to go ahead and make sure they pose as a maintainer, do his duties as a maintainer, and then went ahead and created all the all the required actors that could submit PR requests, all the required details that could mask his intentions. Two More than 2 years of timeline, that kind of shows the kind of commitment that was behind and why this repository was specifically targeted. It's very important to note that this is a dedicated actor that took his time, that took a very refined approach of first socially engineering it and making sure they get the trust of the person who's trying to maintain this repository, and then introduce code that could benefit them in turn. The technical details are a bit they look complicated, but they're actually not complicated. So what happens essentially is that he the malicious code was introduced in this repository with the help of a file that is encrypted and has a specific code inside it, which doesn't look suspicious, but that is only triggered when a certain request from a certificate authority, or which I'll show you in a minute, a certain request with a certain parameters is passed to that executable. And then this specific code is triggered and it compiles another file, which is an essential dependency of this XZ utility. It replaces it with its own compiled version and thereby giving it a dependency. What in turn happens is that when that dependency is loaded, it runs as XZ in the same process. So the system doesn't realize that another process is running. Usually, if a virus or a worm is introduced to a system, it introduces a new file, a new process. But in this case, that was not it, because a new process was not introduced. What was introduced is another version of the same process that's already running. So now, in the end of all of this, the malicious actor, essentially has an open connection that's running at root level, that's not generating another service for it to be detected. So basically, it's going to go ahead and give him access as root with an inbuilt process, which is very dangerous. So you could ideally look up for any IP address on the internet, just guess it in case this was successful. Just guess that IP address, put a default port, which is the SSH port of 22, put a default port and use admin credentials to get into the server. And that's all that you need. you're into any server that's available on the internet. Now, if you look closer, this was the highlight of it. But if you want to go closer, what happens is that they go ahead and CMake or compile the new version of the file, and then replace it in a couple of places, which is uh, here. Sorry. Uh, they replace it in the dependency. So if you go ahead and do LLD minus D for this SSHD service, you will notice that it gives you a file that looks something like this one here. This is the repository that has been introduced for troubleshooting purpose. So the file name is available here. We could see that. Just give me 1 second. Yeah. The file name is under here. This is the file name that was introduced, libelzima 5.4.5. So this version is a bit higher version, which was introduced to patch it. But usually, if you go ahead and check the dependencies for the SSHD, one of the dependency is this file here. And this is the file that was recompiled with the malicious code. Now, because this actor has trust as a maintainer, he was able to push in code without much of a due diligence or much of, dare I say, peer review, and he was able to compile it with the help of a PR request from another actor that he introduced. So it all seems legitimate that it's been validated and it's been used, and eventually it goes through. This file under the library of library direction was introduced, and if eventually the code goes ahead and copies its own compiled version to the original version and just restarts the service. And that's all that it has to do. The moment the service restart, it uses the new dependency, which is, yeah. So it decompresses, removes Junk's data, and tries to add the binary component there and recompiles it and copies the file over. It's very simple again. But this gives a complicated attack. So in less simplified version, what happens is that after the commit, this threat actor introduced an executable malicious code in this configuration, which the configuration is not active, the code is not active. It only gets activated when it goes ahead and compiles it with the help of a request that is sent. The moment it sends it, it compiles the same file again and replaces it with the original file, restarts the service, and goes ahead and creates this scenario where the service now uses the malicious code file. And after that, all the actor has to do is try to get his try to get an IP address and try to extract and try to connect to it. The reason why only the threat actor can connect is because this file and this process is encrypted. That's another genius level of obfuscation that has been done here. Uh, and I'll get into the details of it because it's really interesting. The reason why only threat actor can go ahead and connect it because the request requires a key or certificate, which is encrypted in a key that is only held by the threat actor. There are two kinds of key: a public and a private key. Private key is the key that is held by threat actor. Public is everybody else gets it to read the message. So he encrypts it, sends it there, and the public key decrypts it and executes the code. That seems very simple, and system D, after it gets recognized with the process, it gives it all the access it needs, and eventually they have root access. The reason why it was difficult to find is because it was, first off, the service was hidden. Second, the it was it was only intended for a couple of systems. So they did not do the greedy method. They only targeted a couple of systems so that not to get suspicions too early in the process. They, of course, they would have done more, but in the early times, they did not want to get detected, which is a brilliant strategy if you want to get over the world and get to connect to every computer possible, right? The For example, they only targeted operating systems that have 64 bits or x86 and 64, not ARM or anything else. So as long as the system is this, then the code was activated. So every time a request for connection comes in, it checks, decrypts the code, executes it, and checks this condition. If the system is similar to this, then it goes to the next code. Otherwise, it doesn't. So a lot of computers were not able to replicate it because it felt like it was just a chance coincidence after this detection happened. So the reverse engineering took a little bit longer. The process is part of Debian. So you cannot install this software and assume that this would be similar behavior. This has to be part of Debian. It has to be by RPM packages. That made it a lot more difficult for going ahead and reverse engineering and trying to see what is downloaded and how is it installed and what is it executing, because everything else is done during installation. Yeah, when the installation is done, the system already has vulnerability, and that is a very dangerous scenario. Now, all of this seems worrying, but fortunately, this was found out, and the only systems that were affected were bleeding edge. So if Fedoras and the Ubuntu's and the Red Hats of the world that were running bleeding edge, which is pre-built releases or short-term releases or early releases, they were affected because they were utilizing the new packages. The stable builds were not affected because this package was still not mainstream and it was detected very early. And how Andrew detected was he was trying to benchmark his SSH connections, and during that, he realized that standard SSH connections take X milliseconds, but this was taking X plus Y milliseconds. Upon investigation, he found out that it was running additional processes and it was trying to open backdoor channels, create root level files that were giving access open to anybody who wants to extort it. And that led to this revelation. And eventually, a patch was released, the version was discarded, and now things are pretty much okay. Now, the reason why this also is very complicated is because even though you can prove a backdoor, if you cannot execute that backdoor or cannot replicate it, it doesn't complete the equation. It always feels like that it might not have been what we thought it might be just some other process that is trying to do something and looks suspicious. That's it. And the reason why that was so difficult is because backdoor could only be triggered with an SSH certificate payload that had a very specific key. And that also had a couple of parameters around it. And if those parameters added to certain value, then and then only the execution happens. So there are multiple layers here. First is trying to get rid of a lot of operating systems. Second is trying to get rid if the software was installed after the installation. And on top of that, there is a trigger only dedicated to one particular key. And that's the key of the actor. The researchers eventually realized this and they replaced the key with their own key because the other key would only work if you have the private key. And there was in case you have that private key, you probably are the actor. So in case you don't, then you have to use the researcher's key or the researchers developed executable, recompiled executable, which gives you the key that has values available to us as a researcher, and you could go ahead and send a request. The genius move was that no software usually goes ahead and checks the certificate and its payload. Every utility on the internet that goes around has the ability to carry payloads. Even ping can be sent with a couple of payloads and you could siphon data through it. Certificates also have certain categories and certain spaces where you could put in payloads. And that's what he he or she or the actor tried to use to go ahead and send information if they wanted to connect to that system. They went ahead and the payload was encrypted and signed with the attacker's key. It had three different sections which were used to go ahead and check if the command was to be triggered or was it just a test. So in case A, the equation for A plus B plus A times B plus C, which values are coming in from certificate, the greater than three, the backdoor just skips the process. And that was done intentionally, I think, because sometimes they wanted to leave gaps for the researchers so that researchers doubt their own research. There were many thoughts like this. This repository right here is the researcher repository that is made to go ahead and work and reproduce this. I was I wanted to replicate this, but unfortunately, I had some issues with the Go build process, which isn't working fine with this repository. So maybe we will have to submit a request. But this is the repository that, in case you're proficient with Go and you can troubleshoot build processes through it, it might be easier to replicate this. Essentially, he explains that the certificate that looks something like this has a payload section here. And this is where this payload section gets information to trigger the malicious attack or the malicious code. You can create your own honeypots. Honeypot is basically a machine which can be used to trap hackers and lure in hackers and see what kind of people are attacking you. So you can create a honeypot with this vulnerability also. And it's easier said than done because there's a Go process here that needs to build the executable. But after you've done that, all you have to do is execute this and the process just starts. So you have to execute and compile this repository. The key that the hacker used was this, and the key that the researchers are using is this one. So this one is known, and this the private key for this one is unknown. So basically, we will be using this key to go ahead and connect to the system. Eventually, what happens is that when this connection is established, when you try to compile, when your connection is established after you've compiled the executables that are there in this repository called XZBot, the XZBot goes ahead and creates an executable XZBot again with the same name. When you execute it and give the name of the IP address of the machine that you want to target, it eventually leads you to go ahead and connect it in this way. So all you have to do is just give a default address and the port. Port would basically be 2020, 22 in case of SSH. Whichever you've configured eventually goes through and gives you a connection as root. The root file that the process is connecting to is available under temp folder. And if you notice this, there's a zero, UID 0, which means the root process is available with root credentials. Root credentials are the most powerful credentials on Linux. Nobody actually uses it to log in because it's possible to delete everything with it, even by accident. So if your computer is infected with something and you logged in with root, the same process can overtake the credentials and can be catastrophic. If you notice here, that's the normal process tree, which means something starts and eventually it starts something else. So these are child processes and so on and so forth. Same credentials go through, but after the process is injected with the malicious code, there are more things that come into the picture. There's a process that starts, a sub-process that starts, which has root credentials. If you notice this connection string here, you will see that any IP address with the port can be given in, and the same connection would establish over the internet also. So any servers or any services that are open on utilizing this code can potentially be accessed over the internet. I was planning to give a demo around this, but unfortunately the Go build process did not work out. So I'll pass this repository on the chat in case you want to try it when you have time, and if some of you are proficient with Go. it's a nice exercise. It's very easy, scarily easy to do. So it kind of highlights how crucial this was. Before I go ahead, I want to show you the extent in which this person, the maintainer, was harassed. This website has a chronology of how much social engineering went into the whole process. How much of social engineering went there, and uh, how much of this was well orchestrated over the years. So if you see here, the comments that are mentioned here are pretty much trying to tell him that he's not doing his job, and that he needs more resources and more people. And eventually, somebody is introducing him to somebody else. And there are many actors like this who are going around, but this actor stands out because he's continuously committing resources, and not to any other repository, just to him. There were some red flags, but I guess the maintainer was pretty burnt out, and that's why he kind of caved in. But that is basically it. I'm sorry, I do not have a demo for this. It didn't work out, but I hope you have some thoughts around this. If any of you have anything that you want to add, please do. I'm at the end of my presentation. I'll be sharing the links for the XC repository and the documentation also. Again, a couple of talks that I feel like can help you in setting up the demo. Two of these things, I utilize these videos to set up the demo. So in case any of you is interested, you could go here, and the chronology of the attack. Yeah. So that kind of brings me to the end of the presentation. In case anybody has something to add or wants to say something, uh, that would be awesome. Also, I would move the time for this meetup because I got a feedback that it might be easier to do it during the lunch hour. That's why I changed the time to the lunch hour. I hope it suits you well. And in case nobody has any comments, I thank you for joining me. In case you have any other presentation that you want to work with, that you want to say, please do reach out. I've sent the link on the top. You could submit your sessions, and I'll be more than happy to entertain them.
Thank you so
Right.
much, Mohit, for this informative session, and then I really appreciate your effort. So thank you so much.
Thanks, Raj. Well, that brings us to the end of it. You all have a lovely day ahead of you. Have a good one. Bye.
Thank you. Bye.